Up to this point, we have constructed geometry from structural necessity. Coherence above threshold produces stabilization. Directional variation produces metric structure. Non-uniform coherence produces curvature. Coherence redistribution governs geometric evolution. Finite invariant propagation produces Lorentz symmetry. Dimensional selection stabilizes four effective directions. Threshold proximity explains extreme regimes. We now arrive at a delicate question. If curvature reflects coherence distribution, then what exactly are we measuring when we infer unseen mass from gravitational behavior? Dark matter was introduced to explain curvature that cannot be accounted for by visible mass alone. Galactic rotation curves remain flat where classical mass distribution predicts decline. Gravitational lensing exceeds what baryonic matter can explain. Large-scale structure formation appears too rapid without additional gravitational contribution. The conventional interpretation is straightforward. There must be additional mass. But in our framework, curvature is not sourced by mass directly. It is sourced by coherence-density. Mass is one manifestation of stabilized coherence concentration, but coherence distribution is not necessarily identical to luminous matter distribution. That distinction matters. Let us proceed carefully. In earlier episodes, we derived that curvature responds to coherence density relative to stabilization threshold. Coherence density reflects how strongly a region participates in stabilization. Visible matter corresponds to highly localized, stabilized coherence structures, but coherence may distribute more broadly than luminous mass. If large-scale coherence gradients exist that are not tied directly to baryonic concentration, curvature will reflect them. Observers interpreting curvature solely through visible mass will infer missing matter, but the missing contribution may not be particulate. It may be geometric. Consider a galaxy. Visible stars represent intense local coherence stabilization. But the galactic structure as a whole participates in a broader coherence distribution. If coherence gradients extend beyond luminous regions, curvature at large radius may remain significant. Rotation curves would remain flat. No additional unseen particles required. Now consider gravitational lensing. Light follows geodesics, determined by curvature. If curvature reflects extended coherence distribution, lensing will reflect that distribution. If observers assume curvature maps only to baryonic mass, they will infer additional matter. But curvature need not track luminosity, it tracks coherence. Now pause. This does not dismiss dark matter research, it reframes interpretation. The data indicate curvature exceeding visible mass expectation. The question is whether that curvature must correspond to particulate matter, or whether it reflects non-local coherence distribution within stabilized geometry. Now, consider structure formation. Large-scale cosmic web patterns suggest gravitational amplification beyond baryonic mass alone. In this framework, early universe coherence distribution may have been non-uniform, at scales not directly corresponding to luminous matter. These coherence patterns would seed curvature variations. Structure would form along coherence gradients. Later, baryonic matter would follow those geometric guides. Dark matter would appear to shape structure, but geometry itself would be the guiding field. Now consider the weakness of gravity. Earlier, we derived gravitational strength from stabilization threshold. If threshold scale sets curvature response magnitude, then large-scale coherence imbalance can produce subtle but persistent curvature effects. These effects accumulate across cosmic scale. This is consistent with observed weak but long-range gravitational anomalies. Now consider why dark matter appears to cluster. In galaxy clusters, lensing maps often reveal mass distributions offset from luminous matter. In coherence terms, this may reflect redistribution lag. Coherence gradients may persist after baryonic collision events. Geometry may temporarily reflect pre-collision coherence structure. Observers mapping curvature would infer invisible mass displacement, but geometry may simply not yet have equilibrated. This suggests testable consequences. If curvature anomalies correspond to coherence redistribution lag rather than particle distribution, their evolution over time may differ subtly from particle-based models. Now again, discipline. We are not declaring dark matter non-existent. We are stating that curvature tracks coherence, not luminosity. If coherence extends beyond luminous matter, curvature will reflect it. Dark matter may be a geometric inference error, or it may be partially geometric and partially particulate. Only detailed modeling can distinguish. But structurally, additional matter is not the only possible explanation for anomalous curvature. Now consider threshold proximity. In regions where coherence density approaches threshold from below or above, geometric response becomes sensitive. Small coherence variations can produce amplified curvature. This may produce galaxy-scale deviations without requiring massive unseen halos. Now consider cosmic background observations. Large-scale anisotropies in cosmic microwave background reflect early curvature patterns. If early coherence distribution contained non-baryonic gradients, curvature imprint would persist. Dark matter would be inferred. But again, geometry may reflect coherent structure, not particle distribution. Now, step back. From episode 1 to 15, we have constructed a corridor. Difference to refinement, refinement to stabilization, stabilization to threshold, threshold to metric, metric to curvature, curvature to dynamics, dynamics to minimal evolution rule. Evolution rule to dimensional selection, propagation to Lorentz symmetry, threshold proximity to extreme regimes, coherence geometry to reinterpretation of gravitational anomalies. At no point did we insert dark matter. At no point did we assume space-time fundamental. Yet we arrived at gravitational structure consistent with observation. This matters because if gravitational curvature is geometric encoding of coherence distribution, then the missing mass problem becomes a missing coherence interpretation problem, not necessarily a missing particle problem. Again, caution. Data must decide, but structure permits reinterpretation, and that is enough to justify investigation.